created by Mindsticks Foundation Trust.
Welcome to today's explainer class. Today we're looking at the grouped data mean, solving with the direct method, learning the assumed mean shortcut, mastering the step deviation method, and finally, choosing the right tool. Let's get right into it. Section 1. Understanding grouped data mean, finding the center of our data. You see, when we collect data from large experiments, like recording the heights of all the students in a school or measuring the lengths of fallen peepal tree leaves, we notice something quite fascinating. The numbers often cluster around a specific central value. In statistics, we call this central tendency the mean. But finding it for massive amounts of data? Well, that requires a highly structured approach. Because our large data sets are grouped into intervals or classes, we can't simply use the exact raw numbers anymore. Instead, we have to find a single representative number for each group. We call this the class mark, denoted mathematically as x sub I. Think of it as the exact midpoint of your interval. For instance, if your class interval is 10 to 20, your class mark, your x sub I, is simply 15. This gives us a solid single number to work with for all our calculations. Moving to Section 2, Solving with Direct Method, the foundational formula. Let's observe our baseline tool for finding this average, commonly known to us as the direct method. This is absolutely the most straightforward mathematical approach we have.
This brilliantly illustrates the direct method in action. Take a look at this table showing the percentage of marks for 50 students. In the first column, we have our class intervals. In the second, our class marks, x sub I. And in the third, our frequencies, f sub I. By systematically multiplying each class mark by its corresponding frequency, we get the values in the fourth column, x sub I multiplied by f sub I. We then take the sum of these products, which is 2,840, and divide it by our total frequency of 50. This gives us an exact mean of 56.8. Very simple and elegant, isn't it?
But here is the problem. What if the data numbers are just too large? Notice what happens as our data grows. Multiplying large frequencies by large class marks becomes incredibly tedious. I mean, if you're calculating thousands of data points, doing this by hand consumes precious time and makes us highly prone to unfortunate calculation errors. We clearly need a smarter, more efficient way to handle all this heavy arithmetic.
Section 3. The assumed mean shortcut, shifting our baseline. To solve this problem of generating very large products, let's learn a clever little method to remarkably reduce our calculations, aptly called the assumed mean method. The crucial point here is this new concept of deviation, denoted as d sub I. By intelligently guessing an assumed mean from our data, which we call capital A, we actually shift our mathematical baseline. The formula is d sub I equals x sub I minus A. What this means is that instead of multiplying our frequencies by massive class marks, we only have to multiply them by these much smaller deviations. The algorithm is beautifully simple to follow. Step 1. We strategically choose an assumed mean, A, usually a class mark picked right from the middle of our table. Step 2. We subtract this assumed mean from every single class mark to find our deviations. And Step 3. We multiply those new deviations by our frequencies. This drastically shrinks the actual numbers we are working with on our paper. Let's study a real-world example of 100 vegetable vendors. Look at the daily sales numbers. 1,000, 1,500, 2,000. Multiplying these directly by the number of vendors would be quite exhausting, right? But by taking 2,250 as our assumed mean, notice how the massive daily sales numbers shrink. Look at the deviations in the third column. They become much more manageable numbers, like -1,000, -500, and 0. Now our multiplications are significantly easier to handle. But wait, we have another problem. What if the deviations are still large numbers? I want you to look closely at that vendor table again. Even utilizing the assumed mean method, multiplying a frequency of 15 by a deviation of -1,000 still leaves us with a product of -15,000. That is still some very heavy arithmetic. Surely there is a way we can make it even simpler. Section 4. Mastering step deviation method, shrinking numbers further. Enter our final and absolute most powerful mathematical upgrade from our toolbox, the step deviation method. This brilliant technique reduces our manual calculations to the absolute minimum. Let's see how this builds upon what we just learned. We introduce the step deviation, denoted as u sub I. If we carefully inspect our deviations and can find a greatest common divisor, which we call lowercase g, for all our deviations, we can divide them down even further. The formula is
U sub I equals D sub I divided by G. By doing this, we reduce those large deviations into single digits, making the final arithmetic incredibly simple to solve entirely in your head.
Observe how beautifully this simplifies a complex, real-world problem. In this table detailing health insurance investments across families, our initial deviations in the third column were negative 1,200, negative 800, and negative 400. Quite intimidating, right? But by recognizing 400 as our common divisor, our G, those large deviations magically transform into simple integers like negative 3, negative 2, negative 1, and 0 in the U sub I column. Multiplying a frequency of 15 by negative 2 is just negative 30. You can comfortably do that in your sleep.
2,140 rupees. By applying our final step deviation formula to these tiny numbers, finding the mean of U sub I, multiplying by our common divisor, and adding back our assumed mean, we easily calculate the final mean investment of exactly 2,140 rupees. And the best part? We achieved this precise answer without ever once having to multiply massive numbers.
Section 5. Choosing the right tool, comparing the methods. Now that we've thoroughly explored our complete mathematical toolbox, it's vital to reflect on how these methods compare to one another, and more importantly, when you, as a student of statistics, should use them.
Let's look at a direct comparison. The direct method uses full raw x sub I values and forces us to calculate tedious large numbers manually. On the other hand, the step deviation method elegantly scales the data down using those U sub I values. Yet, the most important mathematical truth to remember here is this. Any valid method you correctly apply will always yield the exact same mean for the data. The math is perfectly consistent. The choice is purely about protecting your precious time and minimizing the chance of calculation errors.
So, which method will you choose for your next statistical calculation? As you look at your next frequency table, I really want you to ask yourself, will you do the heavy, tiring lifting with raw numbers, or will you utilize these evolutionary mathematical tools to work smarter, not harder? Mastering these steps empowers you to handle absolutely any data set, no matter how large, with complete confidence and ease. Keep practicing these concepts, class. You've got this.